Ladies and gentlemen, welcome to today's episode. We have a special guest. All right, this is going to be a very special episode because I met this person when I went to Napa, and it was like a little networking event between Latino executives. Latinos are making shit happen, and I was like, and we had a little dinner, and I met this one woman that a Latina physicist, like a scientist, and we just had the nerdiest conversation. I said, I need to bring her in. And I want to welcome Camila Uzcategui. She's Doctora Camila Uzcategui. Yeah, 32 years old. She has a doctorate. She also has a bachelor's in physics. Right? Like, it's not very Latina. Not very much Latinas have like a physics degree. Like, what got you into physics anyway?
You know, it's interesting. I think the biggest thing is curiosity. I really wanted to understand how the world worked. And, you know, there's all these different aspects of science. You learn about biology, you learn about chemistry, but physics sits at the center of it all. They always say, you know, applied math is physics and applied physics is chemistry and applied chemistry is biology. And it really, you know, connects all these different aspects of the world, and you get to think about it at the most basic level. And I also just wanted to understand people. So I also got a bachelor's in anthropology. So I was at the two opposite sides
So
of the spectrum.
So anthropology and physics all at the same time.
All at the same time.
Wow, why? Like, what makes you like? Because a lot of people like are intimidated with math and physics and stuff. I'm a type of person. I love physics, but I'm gonna be honest. I'm intimidated by it.
Yeah, you know, I got to the United States when I was 9. So me and my mom came from Venezuela, and I was very good at math, but I didn't know any English. So, you know, it's like you cozy up to math when you don't know any English. Because I was like, I knew I was smart. I knew that I was an intelligent kid. But because I didn't know English, I was doing so poorly in the classes, right? And I was in ESOL and I was doing all of that. But when I got to math, language didn't matter. It didn't matter whether I spoke Spanish, whether I spoke English. I could sit down, I could work on the problems, I could get really good at it.
Were you obsessive with math? Is that what it was?
A little bit, because I'm also really competitive. So I was like, okay, I don't know English, but I'm going to be better than you at math.
You're also a CEO of Manifest Tech. Can you explain what your company is?
Yeah. So during my PhD, so I got my undergrad in physics and anthropology, and then I really wanted to apply it. I wanted to apply some of the learnings that I had to, you know, make the world a better place. And I really wanted to focus on making things. How do we manufacture the next generation of products? So I got my PhD in material science and engineering.
Wow. Inteligente esa mujer.
And the University of Colorado Boulder. And we were developing new technology. We were inventing new ways of making products. And we developed a new method of 3D printing. And we decided to spin it out and turn it into a company that's Manifest Technologies today. And
so a new way of 3D printing, is it the 3D printer itself, or they gotta talk to you and you print whatever item they need at a certain specific way?
That's a really good question. So it is the 3D printer itself. So there is, you know, 3D printing was invented in the 80s. It started with, you know, we're going to make something that is a 3D object by just rastering poquito por poquito, layer by layer, and turning it into a product. Over the years, we've invented new materials, new ways of interacting light with materials. And we took a technology that the basis of it is that actually, you know, there's light all over the world, even, you know, light that's shining on our faces right now. There's a wavelength of that light. 405, it's in the blue range, which is really good at getting a chemical reaction to happen. So if you
light makes a chemical reaction.
Light makes the chemical reaction, exactly.
But it's only certain chemicals, am I right?
Exactly, only certain chemicals.
And you're working with those chemicals.
And we're working with those chemicals. And then when light reacts with this chemical, it goes from a liquid to a solid. So we actually manipulate the light to turn that light into a particular shape. And then as we project that light onto a liquid in this cool volumetric way, we turn it into a solid. And the best analogy I can make is, have you heard of a CAT scan? Like a CT scan.
CT, yeah.
You know, you get in there, you know, sit in a little machine and it takes pictures from 360 degrees.
Mm-hmm.
So it takes all those pictures and then it puts them into a software that puts all those pictures together and creates a 3D image. So the doctor can look at it and be like, okay, this is where things are in the person's body in 3D. What we do is we actually take a 3D object and we deconstruct it into all of the angles that would be required to make that 3D image.
Wow.
Exactly. And then we project that back into a volume and then make a 3D part.
So you can make anything with that 3D printer.
So we could make a lot of things, you know. As a scientist, I'm not going to say anything.
Bueno, tú puedes crear una pistola.
Yeah. Depende de la pistola, depende. Tú sabes, hay gente creando pistolas, so I'm not going to say no. Pero with our machine right now, we're focused on medical devices. También podemos hacer los lentes adentro de...
So you could even, because a lot of like 3D printing, you make like regular material, like not de que... so you're also you're able to print glass.
Yeah, so we're able to print a polymer. So it's a plastic that's has similar properties to glass. And we're trying to get closer and closer. So what's nice sometimes about printing a polymer or plastic instead of glass is that it's a lot lighter weight. Mm-hmm. So if you have glasses today, a lot of them are made out of plastic because if you were to put glass inside of those glasses, it would make them a lot thicker and a lot heavier. So yo cuando estaba chiquita, yo usaba lentes, horrible prescription. Y mi tía me decía que yo usaba lentes que eran culo de botella.
Entonces tú estás ciega.
Yo sí, estaba ciega, estaba bien ciega.
¿Y qué pasó? ¿Te hice cirugía o
sí,
contacto?
Me hice la cirugía, también usé lentes de contacto y todo eso.
¿Tú estás usando lentes de contacto ahora mismo?
No. Yo me hice la cirugía, me hice LASIK.
Oh, you good? So
I'm good. I'm good.
I'm about to say, like, do you do the polymer contact lenses?
Yes, I was using the polymer contact lenses, de todo, pero cuando uno estaba chiquito, de repente los lentes eran más gruesos porque están hechos de glass. So because of that, when I would get called culo botella, it's because they were so thick. They were the bottom of...
Man, I would love to see pictures of you as a little...
It was very cute. Also, you know, awkward phase.
Look, she had a glow up.
You know?
The nerdy girls in the class, guys. The nerdy ones. Don't pay attention to the cool ones. The ones that are smart, that's the ones that you look for. All right? But I mean, that CEO, you know, running her own company, super, extremely smart because, man, even as an American, Americans are not going forward to getting a physics degree, right? It is also extremely intimidating. You coming over here to the United States of America, like, siendo un inmigrante a los 9 años, not speaking a lick of English.
Yeah.
To be able to like, oh no, I'm gonna do that. It takes a level of courage and believing in yourself.
Yeah, honestly, I think part of it is also the belief, like, mi mamá, right? Like, mi mamá just at every stage of my childhood, you know, going into high school, going into college, even though it was just her by herself a lot of the time, she was always just like pushing me and encouraging me. Like, even though, you know, you look around and you're like, what do you mean I can do whatever I want? She's like, no. You can do whatever you want.
Oh, wow.
I'm going to be here to support you. I'm going to be here to, you know, give you whatever you need in order to encourage you to do this. She was like, all you got to do is just go to school. Just like, enfócate en la escuela, enfócate en tu educación.
So she motivated you to continue through school.
Yeah.
But there had to be something within you to be like, I'm passionate about this, right? Yeah. Like, I love that you must have loved learning.
Yes. And I still do, right? Like, I think that's also why I wanted to be a CEO, right? I went from being a PhD scientist, spending 14 labs in a lab by myself, 14 hours in a lab by myself, to being like, wait, I want to learn to do other things. Like, how do I bring this technology into the world? How does it actually impact people's lives? And it doesn't impact people's lives in the same way that I wanted to make an impact by staying in an academic journal. Because as scientists, our training is, we do research, we study different aspects of how the world works, and then we publish it. And we publish it for other scientists, for the world in some cases.
Yeah, but I feel like the world right now, no, nadie lee.
Exacto.
Yeah, so it's like an uphill battle. Like,
right.
There's a lot of like attack on education. I don't know if you're saying it. I feel like there's also an increase of people becoming even more illiterate. Right? Like, does that scare you a little bit in a way? Like, man, the future, no, especialmente siendo Latino.
Sí. Yo creo que lo que de verdad me da miedo is more so the curiosity.
Mm-hmm.
Losing the curiosity, because that's really what got me into it. Being curious of how does this work? I was always that little kid that was like, but why? But why?
But why?
But why?
Yeah.
And then it got to a point that like people couldn't answer the why, not because they didn't want to, because they didn't know.
They didn't know.
And I realized that I had to be the person to go answer that question. But the idea of that curiosity not being stimulated in young adults and kids anymore is what's scary to me.
Also, you also think about like these young guys are being told by somebody else. So, people are so quick to be like religion, because when you don't know, you right away go like, oh, religion, this is what the answer is, right? And then, but it's for us Latinos, we just stop it right then and there. Yeah, it just takes something to be like, I want to know what reality really is, because what you study in physics, we talk about numbers, we talk about this is. And then we're talking, like, I'm pretty sure you went into it and you were like, this is fucking nuts.
Yeah. So the first aspect of physics that I really wanted to study is this field called chaos theory, because it was what was at the edge of physics, right? Like if you look at the history of physics and, where we've been the last hundreds of years, you see, special relativity, you see, all of the things that we've learned in modern physics. Then comes quantum, right? Yeah. Then comes quantum physics and everything we've learned there and all the ways it's starting to be applied, right? With a lot of quantum companies coming into the world and starting to apply a lot of these learnings.
Quantum computing. But what is chaos theory?
But then chaos theory was really at the edge of what we had learned in physics. And it was really understanding, aspects like the butterfly effect. What happens, does the fact that a butterfly flaps and wings in one part of the world impact a storm in the other part of the world? Yeah. And we are starting to see those mathematical theories getting applied into weather, for example. So I read a book that was focused on chaos theory, and I was like, I need to be the one that, focuses on the edge of this physics theory. As I started to get into it, it was the hardest math I have ever seen in my entire life. And it was, a mathematical field, pretty much. Gotcha. It was really at the intersection of physics and math. But I thought it was so beautiful. It focuses on fractals. It focuses on, this concept called a strange attractor. The fact that you can, potentially go around a particular, weather event, but not exactly get there. So I was very excited about it. But I realized, I want to work on something that's a little bit more applied. And I have all these tools in my tool shed with learning about physics that I can start to apply to engineering.
Yeah, so chaos. So, because when I think about chaos theory, I also think about, and then you could correct me if I'm wrong. Can it also be like how through chaos things become organized as well, right? Yeah. Is that a part of the chaos theory at all, or, Yeah,
a little bit. So, for example, a great example of that is fractals, right? Like fractals is something that you see both in the everyday worlds, like fractals is the way that your lungs are organized or in a fractal pattern, the way that tree structures are organized in a fractal pattern, but it's still part of chaos theory. So it is an interesting way of connecting.
What do you mean? What does that fractal pattern mean?
So when you think of your lungs, for example, you start with very big bronchial tubes, right? That's how you breathe in the air. That's what's connected, to your mouth. But as you go into the actual structure of your lung, they get thinner and thinner and thinner, but they mirror each other, right? Like the smaller and smaller you get into these really small aspects of the lungs, they look very similar to the bronchial tubes that came earlier. So the fact that you have this organization that's seemingly random, but still exists in such an organized and beautiful way. And I think that's what really attracted me to it. The fact that you had something that could cut across different aspects of reality, both in your lungs, in the trees. There's also
the universe.
The universe.
Because the universe is created through chaos. Basically, is the explosion is just everybody expanding. The explosion of the sun to create materials and creating the earth, and then with this earth, we're creating the moon, and So it's like the beauty of this chaos organizing itself to develop this beautiful universe that we live in.
Exactly.
At the same time.
Yeah. And there's also something so interesting about the fact that you also see it in neurons as well, like in how our brains are actually processing information, which, to your point, it's also like the brain studying the brain, which I also found so fascinating. As you can tell, when I went to school, I was like, I want to learn everything. Like, give me anthropology, give me neuroscience, give me physics. I was like, what is the world made of? And it was really exciting to see that, the more and more I got into it, the more I realized that people wanted to use interdisciplinary work to solve interdisciplinary problems.
This crazy for you. Is it crazy for you to be like, okay, I know all these things and how all these things work? Because I think also the average human being doesn't understand even how time works. Right? And I say that to you, but like a lot of people, and people probably listening are like, what the fuck do you mean by time works? But for you, time means something completely different than the average human being.
Yeah, I never thought about that actually, Gadiel, now that you mention it. But I think it's a tool, right? Like every one of us, and getting a PhD, people are immediately like, eres muy inteligente, you're so smart. But I do fundamentally believe that everybody is smart in their own ways. Like there are so many aspects of the world, aspects of society that I'm not as familiar with. But it is cool that the thing that ties me to the rest of humanity is, understanding the physical world in many ways. And I think the interesting thing about time is that it's something that we use every day, right? You're talking about meet me at this time, how long is it going to take you? This is the timeline, etc. But then when you start thinking about how it then relates to gravity, to interstellar travel, now it starts to get into some physics concepts also, where time is more important.
And also and then a lot of people don't know that we also travel forward in time, right? And for you probably known this for a very long time, right? And it's fascinating to know. They were like, okay, there's times that we are running slower in time. There's human beings on this earth right now traveling forward in time, and they don't even know about it. They're time traveling, right? You already know time traveling is real, right?
Yeah, it's interesting because, as I've gotten more and more into the business world, it's been interesting to apply any sort of scientific concept and be like, okay, how do we talk about it in a popular science sense, right? Like, how do I take a really difficult to understand concept that took me 3 months and multiple notebooks and multiple homework assignments to even start to understand. And how do I talk about it in, a one sentence summary? And I think what's fun about it is to be able to get people to relate to it in a real way of saying like, okay, what would happen if you were traveling at the speed of light? What would happen if a spaceship was traveling at the speed of light? How does that start to impact how you relate to time? And I think that's really fun and really exciting about it, because people are just like, wait, what do you mean? What?
When you found out about this, were you like running around telling everybody, yo, do you know?
Yes,
that time stops?
I was, and it's really easy, especially like en una familia Latina, for people to be like,
Tú
¿De qué
estás
estás
loca. Tú
hablando?
estás loca.
Tú estás loca. ¿De qué estás hablando tú? Eso no es verdad. Just because you read it in a little journal article doesn't make it real.
That's hilarious.
So it's really funny because, I was running around being like, wait, have you heard about these physical concepts that exist that, got written about 100 years ago?
Like the science, it's weird because like there's a scientists already agreed on this, and every scientist around the world believes this.
Yeah.
But when these scientists talk to an average human being about these discoveries that this exists, a regular person would not believe it.
Yes.
Because it sounds so supernatural.
Yes. And it's kind of scary
Yeah.
too, right? Like it's scary to think about that, like lengths mean different things, like, length with height, right? Like if you talk about it, you're like, okay, I know what that is, right?
Yeah.
I learned about that in elementary school. We figured it out. But then when you talk about it, when something is traveling at the speed of light, how does that impact the length of something? People are like, what?
Yeah.
What do you mean the length that I learned about in grade school is different when you're traveling really, really fast? And I think that can be really scary because it starts to open up the fact that we don't know everything. And I think it's very comfortable to sit here and say, like, I know length, width, and height. I know what happens when I, turn on a lighter and the fire starts to go on. Like, all these different things that you can see and you can visualize are really easy to grasp. But when you start to talk about things that you can't visualize or that start to sound like science fiction, you're like, wait, what else is out there that I'm not familiar with?
Yeah, it does sound like science. A lot of it sounds like science fiction, especially like with that they talked about. I saw like this scientists talk about like if you're sitting down and another person is running by and you both look at stars in the sky or both at the same time, you're not looking at the stars at the same time. You're looking days apart or something like that. Can you explain why that is?
Well, there's a couple concepts in there. I think the first thing is that light takes time to travel, right? So when when we're sitting here and we are looking at each other, that's light that's being reflected back onto our eyes.
Yeah.
And it's pretty much instantaneous for the context of this conversation. Light travels really, really fast. However, when you're talking about distances that we start to talk about in the context of light years, that means that it takes a year for the light to travel a particular distance, which means that if a year is the amount of time that it's spending traveling from a location to another location, and let's say that location is 100 light years away, you are looking at light that got emitted from that particular location 100 light years ago. So that means that you are looking at something like that star that you're looking at right now might be dead, might have had some, insane event that had happened to it that is not going to arrive at the Earth for hundreds, thousands of years in the future.
Yeah.
So that's where.
But how come if I'm running by, and we're in the same location, why is it that running by I'm looking at completely different times of light?
So I would have to see what you're talking about. But the thing that it reminds me of is that you are at a different location. So that light is now traveling to a different location and it's going to have a completely different distance than when it's traveling to you versus the person that's running in a completely different location and a completely different speed than you. Then we start to potentially get into relativity, which is what happens when you are, there's like a train experiment. Like if I put a watch on a train that's moving at the speed of light versus a watch that's just like sitting on Earth.
Yeah.
How are those tick marks going to be different? And, the idea that if you put one twin up in space versus another one on Earth, they're going to age slightly different.
Because like the one that space came back young. They did the experiment.
Yes.
And can you tell people like what was the experiment? What happened there?
So I'm not familiar with all of the details, but what I do remember is that the idea was that if you put, and I actually have a few professors that I worked with that ended up sending a lot of samples, like animal samples, into the International Space Station to see what the impact would be. I think there's two aspects. One is what's actually happening with time, right? So what are your cells doing? What are your cells experiencing? Unfortunately, there's the other side, which is the fact that you're in microgravity starts to impact your bones, right? Like the reason that our bones are composed of what they're composed of, the way that our muscles work is because we're always undergoing gravity and being compressed under gravity. You're compressing all of these different, components of your body. So even though, the twin might have experienced less time just because of the, gravitational effects, the fact that there's this space-time relationship that's related to gravity. Now you're seeing the other aspects of the effects as well, which is like what's happening to their bones. So even though, you do this twin experiment and you start to see, oh, maybe this other twin is aging a bit slower, you're now seeing other components of the, microgravity effects, which is impacts on bone, impacts on muscle.
So it's a concoction of everything.
Exactly.
But also like if the twin that's out, because the twin came back and supposedly the twin looked younger than the other one. Right, so it looked like the twin that was on Earth aged faster, But it could be that the twin, they were theorizing the twin that was out in space is actually the younger version because he traveled forward in time.
Right. It's hard to say because now we're getting into
the nitty-gritty.
Now we're getting into a little bit of the weeds of it all.
Yeah.
Because, once you start to travel at certain speeds, it starts to be really, really impactful, or it starts to be less impacted by gravity. It gets to be really impactful. When you're, a twin up in space versus when you're here, those differences, even though they're a lot more subtle than, what the extreme cases are, which is when relativity, becomes really important.
I know that I'm like throwing these questions at your ass.
Yeah.
I'm very curious, and I know that you're like, I didn't even give her like esto es lo que te voy a preguntar, pero pase lo que pase, vamos a tener esta conversación, right? So one thing that's always been tripping me out, right? Okay. And I'm coming up with these questions on the spot.
Let's go, yeah.
Because you're the one, you studied this, right?
Yeah.
I didn't study this. I know from secondhand, and I got books here and there, but there's certain things I'm like, I read books and I don't understand. I was reading the Brief History of Time by Stephen Hawking, and I was reading it, y yo no entendía nada, ni mierda. I lost the book. As a matter of fact, I just bought a new one because I was reading it in the plane. I was like reading every page. I was like, I still don't understand what I'm reading, but I'm going to read this till I understand what the hell's going on here. Right? So what confused me is because, all right, maybe you could explain this, right? And I know people are listening like, wow, they're talking about a lot of science shit. But this is why I brought you here.
Mind you, that was me reading some of my physics books.
Yeah.
I was like, okay, I'm going to have to,
¿Qué es lo que está pasando aquí?
Exacto. Little by little, though.
Okay, so one thing that I'm confused about, right? So they talk about that the greater the mass, right? The stronger the gravity, the slower time is.
Right.
Because time is equates to space, right?
Yeah.
So why is it that, let's say the closer you are to gravity, the stronger there is gravity, the slower time, the time correlates to space. It's space-time. It's not time and space.
Yeah.
Right? So I believe that. Right? I dug into that. I'm like, okay, cool. Yeah. Okay. Time stops in the center of the black hole because the gravity is so fucking strong. Right? But how come it's the same thing when it comes to traveling? So you're traveling the speed of light, also time stops. Like that's one thing that threw me off because I already adopted this idea that gravity, and I'm not saying that both can't be true.
Yeah.
Right? But it kind of messed me up because I'm thinking, the whole time I'm like, okay, gravity stretches time, right? But how come traveling the speed of light stops time?
Well, it doesn't necessarily stop it. It just changes it. So there is a relationship. And now, this is where I'm like, maybe you should have given me a little bit to prepare, Gadiel. Because I haven't studied physics in like 10 years at this point. But from what I remember, it is related to the fact that in special relativity, you have this idea that, actually, let me step back a little bit. In physics, we have different types of physics that we talk about depending on the size and the speed of things. So when things are really, really big and they're really, really slow, it's just classical physics. It's like Newton, like force equals mass times acceleration, just like all the physics that we feel comfortable with. When you throw a ball in baseball, it has the trajectory that we can expect. These are very, very, big and slow things. Once you're talking about big and fast, really, really big and fast things, that's when you're talking about gravity. That's some of the physics theories that we're still trying to figure out how to connect, gravitational theories all the way to quantum. That's still a really interesting field that's being developed in physics. And then when you talk about really, really small things moving really, really fast, or even large things moving really, really fast, you start to talk about special relativity. And that was, what Einstein won a Nobel Prize for. And that's the idea that when things move really, really fast, you start to get concepts like length contraction, time dilation. So time is starting to change depending on how fast something is moving. And
so time is actually changing?
Yes.
Or is it our perception of time?
Well, it's our perception of time because we're measuring it. So everything, all physics is, and that's what's funny and interesting about relativity, is that the way that it was discovered actually was by doing a thought experiment of measuring time. Because that's our only interaction to the physical world is by measurement. That's pretty much, what we do as scientists is we observe something and we measure it. So this idea of relativity was actually figured out by trying to do a thought experiment of saying, okay, what happens if I put a clock in a train that's moving really close to the speed of light versus a clock that's on Earth here? And I think those are the type of experiments that start to not observe, but hypothesize what would happen. So how do we experience time? And the person that is in this theoretical train that's moving at the speed of light is going to experience time in a completely different manner than the person that is just standing still on Earth.
So that means that so what I'm guessing that the person on the train is going to feel it instantly.
Well,
right?
They're going to feel what they're feeling at a completely different time experience than what you're feeling. So the way that you kind of do that experiment is just by comparing those clocks. Okay, we put a clock here and we put a clock over here. Let's run that experiment.
The Cesium clocks.
Exactly. And then let's put them back together. Do they have the same spot?
Yeah. Okay.
Like, do the hands on the clock look exactly the same or do they not? So I think that's the experiment that you're doing to try to figure out what is happening. But then I'll tell you the other, area, which is really, really small things. And that's when we got into quantum. So those are the different, components of physics that we're still, trying to all make work together. Because the theories in physics, they're not theories because we haven't proven them, but they're theories because we're saying, okay, this has
been proven over and over again.
Exactly. This is what we show. We can't do the same ball in a trajectory experiment, but from the experiments that we've done, they all agree with each other.
Yeah.
But in physics, we're still trying to figure out a way for the gravitational theories to agree with quantum, for example. Even though they've all been proven separately, there is this idea that we are going to have physical theories that are extremely able to just agree with each other on every single aspect, when things are moving really fast, when they're moving really slow, when they're really big, and when they're really tiny. And we're still studying how to do that.
So if we're moving fast, does that mean time is slowing down?
So
I mean,
So yes and no, right? Because it, again, like to move as fast as the speed of light
yeah.
requires
Maximum, yes. As a mass, you can't travel that fast.
exactly. Yeah. So in those cases, that's when we start to observe time dilation, length contraction, all of these wonderful theories that we have. We start to observe those in those extremes. But as a human being, the idea of traveling at the speed of light is not something we can do
That's
today.
not possible. But how fast do we need to travel? Like, if I'm driving in a car, like, let's say we're on the plane is going 700 miles per hour.
Yeah.
Is time slowing down because we're traveling that fast?
It's still too slow. Like the speed of light, think of like going orders of magnitude faster than a plane.
Yeah. It's like, I think it's 186,000 miles per second.
Yeah. Something that is so extreme that we can't even possibly, we can't even grasp it. And the impact on you going in a car is so minimal.
Yeah.
That it doesn't even it's
not going to affect it.
Exactly. It's negligible, as we like to say.
I saw an experiment. Stephen Hawking had a show. I don't know if you saw it. I forgot the name of the show. But he had two groups, right? He had one group that he wanted to show that we travel forward in time, right? And he grabbed one group and he put them up in the mountain in Arizona. It was like 6,000 miles above. And there was another group that they synchronized these two cesium clocks. One of them stayed ground level, the other one 6,000 high. So after 24 hours, the group that was down at the ground level brought up their cesium clock and they put them right next to each other to see how. And for all you guys that don't know, cesium clock is like the most accurate clock there is. And what they noticed is within 24 hours, the people that were up 6,000 foot above was a millisecond faster, which means they travel forward in time than everybody else in the bottom, right?
Well, the travel, this is because of my scientific training, Gadiel. Yeah. I'm not trying to be like, but.
No. That's why you're here. That's why you're here.
I have to give exactly, the whole, when they bestowed me the PhD, they're like, you must use accurate language. So that's why I'm being a bit of a stickler. But yeah, so they did have an impact on that clock, whether we call it traveling forward in time or I'm like, we can make that a colloquial way of talking about it, but it's impacted by gravity, right? Because your gravity that you experience at a mountain that is so high is going to be different than the gravity that you experience, close to sea level, for example. So then that's how you start to talk about okay, that's that space-time relationship that we're starting to see.
And you were talking about earlier about like things feel scientific, right? Like science fiction, right? And I think one thing that I've always been struggling is that when I met her, right, we were sitting down, we talking about a whole lot of stuff, and we started talking about we ended up talking about parallel universes. We went to a whole nother world. I think we started a new parallel universe that day.
Exactly. Yes.
We had a universe of our own, right? And I think I know that this is a theory, but it's hard for me to grasp this whole concept of parallel universes.
Well, you're not the only one. It's hard for the physicists to grasp the concept of parallel universes, and the fact that there's a lot of studies still going on, with folks that have studied physics for much longer than I have. And, I definitely don't want to step on those toes. But, to give you a little bit of context in terms of, what we're seeing today. So there is this, really beautiful aspect of physics called quantum physics. And that's when things are really, really tiny. What's happening at the tiniest possible scale. And this is the atomic scale in a single atom, single photon, which is the molecule of light. So, when you talk about light, the light that's, again, reflecting onto your eyes, how is that getting to your eyes?
Yeah.
Through a molecule called a photon.
Yeah.
Every single material that we're interacting with, all of our bodies are composed of atoms, which, make up the elements on the periodic table, depending on, what that atom looks like, what the protons, the electrons, the neutrons, all of that.
And how they move. It's like study of also probability.
Exactly.
Which for you guys that don't know, Einstein hated quantum mechanics.
Yes. He famously said, God doesn't play dice. And, many years later, folks like Bohr, have gotten quantum to where it is today, and some, really amazing scientists that continue to study quantum physics. And, what we see in that is probability, right? Yeah. That, we have a particle can also be a wave, and all of these different concepts that we've started to learn as physicists, that, we learn as physicists in undergrad, is extremely interesting because you start to see where things, break down from classical physics, right? If you throw a ball onto a target, it's always going to be a ball. Yeah. It's never going to turn into a wave. That would be insane.
And you were talking about this experiment, which was the split theory.
The double-slit experiment.
The double-slit experiment. Can you explain what that is?
Yeah. So the double-slit experiment is an experiment that was done early in quantum physics research to try to understand how a single particle would interact. So the idea is that if you have a single slit and a particle behaves like a particle, when you throw that particle, it is just going to go through the slit, and if there's a detector on the other side, it's just going to detect like if you were throwing a baseball through a door. Yeah. Just a bunch of balls somewhere in the middle of that, and that would be the expectation. The double slit experiment is the idea that if you put two slits, so let's say you have two doors and you're throwing a baseball, it's either going to go through the right door or it's going to go through the left door. So, if you do that experiment over and over and over again, you are going to get an aggregation of the two different sections of where that ball hit on the other side where the detector is. But instead, in the double slit experiment, you actually got a fringe pattern. And a fringe pattern was very weird because you would say, okay, if I'm throwing a baseball, there is no way that I would get a fringe pattern. How would the baseball go behind the wall where there isn't a door? That doesn't make any sense.
So to be clear with people, what she's talking about, the baseball are photons.
Yes.
So
photons, electrons. Yeah, any single particle.
So the experiment was that he had a light bulb on one side, right, and then he had a slit through one of the paper, and the two slits, and then when he was there, the particles were acting a certain way; they were going straight.
Yeah.
So you're saying, when he wasn't there, when you said the fringe, right?
Yes.
Was when there was more slits on the end of the paper. I think they had like 4, 5 more or something like that.
Yes, exactly.
Right? Which was weird because at first it was like when he's there, there's only 2 lines where the particles travel to, but when he was gone, there was 5.
Yeah. So it's very similar to that. I'm not gonna keep going into too many of the details, but generally, exactly. When it was observed, so the idea of observation, the idea of somebody doing a measurement onto something is actually what creates one pattern or the other. Yeah. So whether you have a 2-slit expectation, which is like you expect these particles to just act like 2 baseballs, or when you have this other case, which was quite odd, which was the fringe. Yeah. When they saw that fringe, which is, many instead of just 2 aggregation of spots, they saw many, let's call it 5. 5, yeah. They were like,
Why is this? It doesn't make sense.
That doesn't make any sense, you know? Yeah. Like we're not doing a curveball with these particles. So the only way that could be explained is if these particles were behaving like a wave. Yeah. Because if you've ever been in an ocean or in a pool, if you hit your hand on the top surface of the pool, you see how those waves move across a pond, move across the water, and move on that surface. If you do it 2 times, then those interfere with each other
and create more waves.
That's
what they mean
those
by
waves have peaks and valleys.
Yeah.
So those peaks and valleys were actually that fringe pattern that they saw on that detector.
Oh, I like that.
So that's when they were able to prove.
But what they're trying to say is that they because they were observing, right? Is it because they were observing, or is it because their presence were messing with the photons?
So that's actually a great question. The idea is that the observance, so the observer effect, is that when a particle is not being observed, it's just a probability, and that probability can be treated as a wave. So pretty much saying, probability, have you heard of a bell curve? So a bell curve in statistics, it's like you have something that's really likely in the middle, and then it falls off to least likely. So before you observe this interaction, the idea is that there's a probability that it's, somewhere, it's going to land somewhere in this location. And that's it behaving like a wave. It's a wave of probability. It's saying.
And how does that connect with parallel universes?
So this is much longer conversation. But right. But the idea is
I told you we're coming to have nerd talk.
Yeah, nerd talk only.
I want to have nerd talk in this podcast episode.
Yes. So the idea of parallel universes has come from the fact that, if there is a probability of, let's call it a particle, right? Whether it's a particle, whether it's a wave, it's a probabilistic function which we're dedicating to it. We're saying, rather than the fact that this is only ever going to land, whether it's through the right fringe or through the left fringe, there's a probability that it's going to land in either. And as soon as you observe it, you lock it in and it lands in one. So that's what starts to open up parallel universes and string theory and all of these different, further physical concepts that are starting to get studied and have been studied for many years as well, of, okay, if at first we start with just a probability of locations and then we lock it into one, what happens to the other probabilities? What happens to all the other potential locations?
That could happen. That
could have happened.
So are they saying that we have parallel universes because, probability can happen, but are they saying that these things are still happening?
So that's a question. So nobody is saying it like, yes, for sure, right? Because that's, again, we try to be really accurate with language and saying, like, I can't tell you there's 100% certainty there's parallel universes, right? But it's a theory.
But this theory, like, majority of scientists believe this theory should be true. Or is it like, is up in the air, like, we not for sure?
I think because we all get the same training, which is like, hypothesis, experimental method, scientific method. It's hard to say where everybody stands. I don't think I have survey numbers at the top of my head. But I think the interesting aspect about it is that you can see it being correct, of, the fact that we have quantum physics and that we have this probabilistic state, and the fact that, we do all these thought experiments around, my favorite physics thought experiment. Have you heard of Schrödinger's cat?
Yeah. Yeah.
So Schrödinger's cat is, so Schrödinger was a physicist, a really important mind in quantum physics. And he created this thought experiment saying, okay, well, there is a cat inside of a box with some sort of nuclear, something that would kill the cat, let's call it. And we don't know, because it's this quantum object, we don't know whether it's going to kill the cat or not. But it's in a box, and the box is enclosed. And you're not going to find out whether the cat died or whether it lived until you open the box.
Yeah. So
when you think about a parallel universe, is you're saying, okay, well, for a second before I open the box, there's two realities that exist.
It could be alive and it could be dead.
It could be alive or it could be dead.
Yeah.
Once you open it, you break it down.
You have the answer.
And you have the answer, and that's it. You observed it, you have the answer. It's dead or it's alive.
So, but does that mean that there's a split within the universe and going like there is probably another universe that the cat is dead?
Potentially. It's hard to say.
That's wild.
Yeah.
That's hard to wrap your head around.
Mm-hmm.
I also heard that they also talked about how infinite the universe is, how vast it is, how many, because there's so many stars, the probability for there to be another Earth and it could be infinite, right? So the probability is so infinite, the universe, that there's also a probability to even have multiple Earths, multiple yous, multiple me's, right? Living with this a different reality than what we're living today. You know, and they also talk about like also quantum entanglement, that person or that it's like another entity or an electron that could be in a completely different universe still connected to us in a certain type of way. That's wild.
Yeah.
That's crazy.
Yeah.
It's science. It sounds like straight up science fiction.
Yeah. Yeah. So some of it is science fiction, right?
Is it science fiction?
So some of it is because we haven't proven it all the way yet. Like the idea that there is another Earth potentially with, you know, a same exact version of us. You know, there's been some amazing science fiction movies that, you know, discuss that concept. But quantum entanglement is very real. Yeah. Right? So it's like there is a beauty of the fact that you can look at a scientific concept that's very real, that's actually being applied today. You know, there was a company that I went to visit this week focused on quantum entanglement and using it for, you know, new layers of security and encryption. And they're literally using photons to, they're creating two photons that are entangled with each other. And one is being used to go through the fiber of the internet. And the other one is being held to study. And if that one is messed with in any way,
it changes the
other one. So that's being used and applied today. So those, you know, quantum theories that existed are now starting to be applied and are very real in, you know, the physical world today. Like entanglement, this idea of spooky action at a distance is, you know, what they called it when, you know, this photon changes in any way, the other one is going to be impacted.
Is it saying that if it's impacted, it gets impacted in the opposite way? Am I right?
Yes, in the same way.
In the same way?
Yeah.
So let's say one photon goes positive, the other one goes positive too, or that one
so it's about spin. So they like spin in a particular way. So they'll, you know, if one is facing in one direction, the other one will face in the exact same direction.
I also heard with the split theory that you were talking about earlier, when they start acting different, right, with the waves, is because, or at the moment that they're acting straight, right, that's when they're supposedly getting disentangled from a different photon. Is that true or not?
So not necessarily, because entanglement, as soon as two are entangled, you can't do anything about it.
They cannot get disentangled.
They cannot get disentangled unless one of them like decays and dies, like for example, or like is, you know, they can't really be attenuated, so or amplified. So if they're attenuated in some way and something happens to it, then, you know, it's gone. But as soon as two particles are entangled, that entanglement is forever.
Woo! What do you guys think about this episode, huh? You know what? What do you guys think about this? This is for me. This is great. I'm having the time of my life right now. All right.
So how did you get into it, Gadiel? How did you start learning about physics, and how did you get excited about science?
Yeah, I think you know, I was very big in religion, and my sister's gay, and I was told that she was gonna go to hell, And at that time, I was like, oh, she's going to hell. I'm going to hell with her. I'm not going to believe this. Because if my sister at that time, she was very depressed. So if I went up to her and saying that homosexuality is bad, if she continues down this path, or that Jesus will take it away from you, I knew that I was going to lose my sister. Like, she was she's some person that gets depressed and might be suicidal. So I'm not going to lose my sister over my faith. And my sister's more important than my faith. And so I was like, if she's going to go to hell, I'm going to hell too. Right. And I said that while I walked away, people were asking me, like, what are you going to do now, Gadiel? And I said, I don't know. Like, how you think things come about? I was like, I don't know. So when I put the same idea, like when I went to Christianity, I went in like, reading the Bible every day. I did Bible studies. I was that guy that would be like, yo, we have a party. And people come into my house and be like, all right, we're going to bust out the Bible.
That's amazing.
Right. But when I got to the homosexuality part, you hear, oh, yo no puedo decirle esto a mi hermana. No, I will lose her.
Yeah.
So when I walked away from religion, I was like a brand new slate. I did not know how the world works. I'm like, how come I don't know how the world works? What is science saying? What is science saying? We're like, how does this earth come about? How old is this earth? And people are like, where do you Gadiel, where do you think we came from? Who created us? I was like, I don't know. Mm-hmm. What is science saying? And like, what is the Big Bang? How does that come about? So I started reading about the Big Bang and how things work, and that the sun and the elements in the sun created Earth. And it was like the Earth is 4.5 billion years old. I didn't know that. The whole concept of time, and like that time stops in the center of a black hole, and that shit is real, right? I think I was fascinated. Like, I need to know more about this. So I'm like, I felt like I was duped for so many years because I felt like I knew more about something else than reality and what has science discovered. And I did feel a certain type of way, like I've been deceived in a way, right? And I think I fell in love with physics. Oh, this is what physics. Oh, this is what works. Oh, and I started watching shows. I bought these books on the brief history of time, and I was like, Stephen Hawking and all these guys, Neil deGrasse Tyson. Like, I got their books. Carl Sagan, Cosmic Connection. And I was like, oh my God, this is great. And the average person doesn't know this. This whole, even when we talked about time, I'm pretty sure you were mind blown.
Yeah.
How was it when you figured all this shit out? I'm pretty sure you were like, holy shit, ¿tú sabías esto? Didn't you run home? You probably ran home and you talked to people like, yo, ¿tú sabías esto?
Yeah. And they still were like, okay, anyways. They're like, okay, go back to your books. Call me when you have a job. And I think that's the other thing. Like, going into physics as an undergrad, it's so exciting. It's so, you feel like, similar to how you felt, like you feel like you're like, what? Yeah. People didn't know about this. People, and this has been information that's been published, that's been researched again for years, for a long time. And the fact that, I was learning it in a little classroom in Miami, and I was like, why isn't everybody here?
Yes.
Why isn't this like a gospel, right? Why aren't we filling stadiums of people wanting to know this? And I think very similar because it's so exciting. Yes. And it's so much fun. Like, I think it brings out the kid in me because when you look at science fiction, when you look at movies, I've always loved movies, you start to see a glimmer of hope in physics in a way that, maybe something like studying politics or studying history sometimes can do the opposite. Yeah. Whereas physics tells you a little bit about what is possible and what is something that is, like spooky action at a distance, all these weird concepts that you're like, that can't possibly be real. And then you learn about it and you're like, oh my God, it's real.
It's
like,
real.
This is really a thing.
Yeah. Oh, that's awesome. Yeah. That's so awesome. Yeah. I know that I saw you light up. Right. And we sat down. When we met, I sat down and I was like, yo, I'm gonna eat arugula. I don't like arugula, but I'm gonna have to eat it because I need magnesium. I was feeling tired as hell. I need magnesium. And you're like, magnesium?
Like, why are you talking about magnesium?
What are you talking about magnesium? And I was like, I eat tomatoes too because it has lycopene, and I don't like tomatoes at all. And you're like, I never thought about that. I'm a scientist. You're like, you're a scientist? And you're like, yeah, I got my physics degree. And you lit up. I felt like you turned into like a little girl at that moment.
Yeah. It's because it's so fun to be able to talk about how the world works.
Yeah.
And with somebody that is also as excited about it.
Yeah.
Because I think, to your point, when I went back to my family and I was like, oh my gosh, have you heard about time dilation? Have you heard about modern physics? Have you heard about quantum physics and the fact that there is, that particles can actually like jump through material? Like there's all these crazy things that are happening at these like really tiny scales that I was like, this is the craziest things I've ever heard.
Do you ever feel lonely knowing all this sometimes, and like it's hard to have a conversation because you can't talk to an average person about this?
Well, sometimes, but honestly, I think, it lit it back up in me talking to you, right? Because as I said, I haven't been studying physics in 10 years. I, became an engineer, have really focused on materials and kind of things that are in the classical physics world for all intents and purposes. We do work with light, but we work with it in a very classical way. You know, we're not doing experiments that are changing entanglements or doing anything like that. So talking about, what initially got me excited about physics is awesome. And I think the loneliness sometimes comes from not being able to talk about it, but people not caring about how it impacts their lives, right? Because physics impacts your life every day.
Every day.
The way that we use a computer, the way that we communicate over the phone, the way that you watch TV, like it is all impacted by physics and light. The way that you get information, those ones and zeros that come onto your computer, it's all physics, it's all light, it's electrical engineering. It's, some of these concepts that I learned many years ago from a theoretical level, but then now get to see being applied in a very exciting way, even with this, quantum company that I was mentioning. So it's really fun to talk about it from a, wonder perspective, because as I said, I think what I'm most excited about is instilling curiosity, right? Like I'm able to give you broad strokes of, what I remember, what I, still think about from an excitement perspective. But I do encourage everybody, if anything spoke to you, go read a book about it, go watch a YouTube video. And, when I was learning physics, I really struggled. I was so good at math, but physics is counterintuitive. What do you mean speed of light changes how time works? What do you mean gravity changes how time works? What do you mean particles act differently when you're observing them? That's very difficult to grasp. So I had to figure out new ways of learning. I couldn't sit in a lecture because I would sit in the lecture and somebody would be telling me about it. And then I would be like, yeah, I kind of get it. And then I would go home and do the homework. And I was like,
especially I think that's something that scares the hell out of me, because now you talk about you need to know calculus, you need to know, and it is all intertwined. Physics is like next level, which is intimidating.
Exactly, it's super intimidating. So finding ways and finding people that can describe it in a new way is amazing. Like there's so many YouTubers, there's so many science communicators out there that you go on YouTube, you go on Google, go on anywhere and say like, explain quantum physics to me like I'm in elementary school, and there's people doing it, And at the time when I was an undergrad and I was learning quantum physics, the best quantum physics book, Griffith's very famous quantum physics book. It is like hardcore, homework problems, all of it. Everybody, if you're a physicist out there, you've heard of Griffith's before.
Okay.
You know what book I loved?
What?
Quantum Physics for Dummies.
Oh yeah?
That book, it was amazing because it was like, let me take it back to something that, you can relate to. And at the time I was really ashamed because I was like, wait, Why can't I understand it like everybody else from just the lecture or from the same book that everybody's learning from? And then I started to learn about mental models. Like, have you heard of mental
No,
models before?
what's mental models?
So the idea of mental models is that based on who you are, based on how you grew up, based on, where you are in your trajectory of life, you're going to learn differently. So, whenever you hear people being like, oh, I'm not a visual learner, or like, I have to learn by doing, or I have to learn by, just, listening to a podcast, for example, we all have different ways of learning things. And with physics in particular, that can be really impactful. So there's actually a whole line of work focused on physics education research.
No way.
Where researchers are just doing work. There's really great work coming out of the University of Colorado Boulder and Florida International University's physics departments talking about how do we teach physics in a way to engage more students? Because if you look at the statistics, physics 1 to physics 2, those are weed out classes. You start with, hundreds of students and get, tens of students that end up going into a physics degree. And as a result, it led to this huge field of physics education research looking at mental models, saying like, wait, why do some people learn by just sitting in a lecture? And why do some people not learn anything at all that way? And understanding your own mental model, like, how do I learn? How do I like to, intake information? Do I need to do an experiment? Do I need to, play with Legos to figure it out? Do I just need to close my eyes and listen to a professor? Do I need to do a lot of homework? Those are all different ways of learning. And I think that was really helpful for me. That allowed physics to become more accessible.
That's so cool because I feel I'm not gonna lie. I learned about. I didn't learn physics in school. I never taken one physics class, right? And as an adult within my 30s, when I learned what physics was and quantum mechanics and stuff like that, like I do feel a certain type of way. I feel like I was cheated, right? I feel that there is a pain inside of me that I'm like, man, I wish, I went to public school. I wish I had the opportunity or the ability to be like, I wish I would have taken this class. I wish it was provided to me or it was taught to me, right? But now as an adult, like it does feel like it's a little late to learn the intricacies of physics and stuff like that. But I still will, you inspire me. I kind of want to go back and be like, let me at least get an undergrad in physics, right? But knowing what it was, because at that time I didn't know what it was. For me, I thought what physics was like another level of calculus. And everybody talks, it's going to be hard. It's going to be hard. Calculus is hard. And I was like, oh, math is extremely hard. And then for me to understand what this is as an adult today, I do feel cheated. And I'm pretty sure there's a lot of people that feel like that, especially growing up in public schools and lower income, right? And it feels like there's I wish I would have had that type of privilege to be like, oh, por lo menos I had the option to learn, or they taught me this in class.
Right.
Yeah,
and it's interesting because there's also a relationship to value, right? Like, I remember growing up being told, like, if you're not a doctor, a lawyer, or, an engineer, what are you doing? That's the only way you're going to be successful, right? So, I think there's the arts, right, that sometimes feel accessible when all you're getting told is, like, you need to be a lawyer, a doctor, or an engineer to, be worthy. But there's also just the hard science of, like, science for the sake of doing science. Like, there's fundamental scientific work that is not going to have a return on investment for 50 years. If we talk about when quantum physics was studied, it was a very long time ago, and we're starting now to reap the benefits of it. But the value of it is so high, and yet is not considered something that's very sexy or very interesting. They're like, why would you go be a physicist?
Yeah, but this is also the thing that's the most important, because we're talking about we want to advance the human race.
Right.
Like the works that people did in the past, we're taking advantage. Like Isaac Newton. If there was no Isaac Newton, where would we be scientifically today?
Exactly. And that was all as a result of somebody just being able to ask questions.
Yes.
Ask questions about how the world worked, not how is this going to, help me sell the next computer?
Yes.
Right? Like, that's not the questions he was asking. He was asking, why does that happen?
What does that happen? Yeah.
Why does that happen? Why does this work in this way? What if we did this versus this?
Yes.
And I think that's something that's so special. And I do encourage you to, dabble in it a little bit more, because I think similar to mathematics, like in math, it is a language, right? Learning a language is hard.
Yeah.
It requires a lot of practice, a lot of repetition, a lot of understanding, a lot of application. When you're learning a language, okay, let me say a sentence this way. All right, what happens when I use slang? That's the same as math, right? Like, let me do it the super hard, way that we've done it all the time. But then there's also kind of math slang that is like, oh, here's a little shortcut.
Yeah.
Here's the quadratic formula, helps you solve this problem a little easier. Use the quadratic formula. Don't just do it, just by hand over and over again. So there are these components of math that like you do have to learn to understand how to apply it to physics. But it's like any language. And sometimes it feels really inaccessible to, low-income kids, to, kids that are just like, wait, what's the point of this? Why is this useful?
Yeah.
Where it's like, it's useful because it lets you speak a new language that allows you to talk about physics.
I think you also peel the fabric of reality and be like, it peels the fabric of the universe and be like, okay, this is how things work.
Right.
The answer is always in math.
Yeah.
That you could get rid of all the physics books. We could grab all the books and all the scientists' research. We could burn it all up, get rid of it, and guess what? 1,000 years from now, a smart, intelligent species or even human beings will come up with the same theories all over again. Yeah. It will happen again because this is what reality is.
Exactly. And maybe the math would look completely different, right? Different symbols. These are all just symbols we came up with, right? We use a bunch of Greek letters to, symbolize this, symbolize that.
Yeah.
So it's like the symbols would be different, but the theories would stay very, very similar. And I think that's what's exciting because it also brings us together as human beings, right? Like, it doesn't matter what you believe.
Yeah.
It doesn't matter which God you believe in. It doesn't matter what you do on December 25th. If you throw that apple up in the air,
it's going to come back down.
It's going to come back down. It doesn't matter.
I made her watch this documentary. I feel bad because we went off and talked about physics. I didn't know we were going to go there. I was like, yo, watch this documentary. I had her watch the Detox, Plastic Detox. Yeah, and I cannot have her on the podcast not talk about it because they hit me that because I want to talk to you about it. I didn't know that we were having a full conversation about everything else. But I saw this documentary called Plastic Detox, right? And you deal with materials as well. And I know that for me, just to give a background, it's about people detoxing and how chemicals like plastics is affecting our bodies. And we're seeing a lot of people. So within the documentary, there's 4 couples or 3. There's 3 or 4.
It's 5. Then,
5 couples. They're trying to have babies and they cannot have babies. So what they're doing is that they're trying to get rid of plastics in their life and how plastics is affecting their bodies, like sperm counts and stuff like that. Right. And in the end of the spoiler alert, the end of the documentary, they all got pregnant. They all got pregnant.
I think three of them. Yeah.
3 of them. Some of them, not all of them. Right. So I know you study a lot with materials and stuff like that. And they came up with a concept of green chemistry, which is like the study of how can we use chemistry for good to be more green, and so people could have an understanding because they teach chemistry, but they don't understand how chemistry affects environment, the body, and stuff like that. So that's why I was like, I thought about you immediately when I saw that documentary. And so, what do you thought about it? Have you studied that green chemistry? Is it a thing?
Yeah, so it is starting to become bigger and bigger.
Yeah.
So I'm not a chemist. I'm a materials engineer by training, which, to give a little bit of that distinction.
Okay.
It's that, we will take learnings from chemistry and then apply it to some sort of material. So the focus of my PhD was really around, okay, how do we use materials that can go into the body really well, or that can perform a particular task really well, whether it's, bending light. That's what glasses do. They bend light in a particular way so then you can see it.
Yeah.
So, my training wasn't in chemistry, but it is something that's becoming really, really important in the training of chemists. And it's not just in how the chemistry is actually invented or, what are the paths that we're going through to get, a final molecule, but also how we do science in general. So green chemistry actually spans all the way from, how are we synthesizing these molecules? What are the molecules that we're creating? How does it impact the world, the body, all around? But also, what are the practices that we do in the lab, in the laboratory, in order to make sure that we're not harming the environment,
or harming
people, and just, the idea of environmental health and safety. How do we ensure that we are getting rid of waste appropriately? So green chemistry actually spans a lot. So not just in the synthesis of those molecules, but actually, how we're doing and performing science at the bench level.
When you saw the documentary, did you ever feel like, oh, I got to get rid of all my plastics?
So, a professor once told me that there was, the Bronze Age, there was the Stone Age.
Yeah.
Now we're in the polymer age, right? Everything around you has some sort of polymer in it. And the reason I differentiate between plastics and polymers is because, plastics has become kind of a bad word of just like, oh, that has too much plastic. And I think the negative connotation is appropriate in many cases, right? This documentary talks about bisphenol A, BPA, right? Like, and all the impacts that it has had that we couldn't have predicted. But there are some really great polymers out there that have been designed to be really helpful for medicine. For example, if you've ever gotten stitches that dissolve in your body, that's a polymer, right? So there's so many different types of polymers. So, just putting them all in the plastics category can sometimes be really difficult, because back to that green chemistry, there are companies, even, companies of some of my friends that are doing some amazing work to make polymers that are
biodegradable,
that have properties that make them, last longer than other plastics and other polymers. So they don't go into the environment. So they're not wasted in the same way. So something that's been really important to us in our company is to think about the life cycle analysis of our products. What happens at the end of life of something, right? When you talk about a water bottle, it's really hard to think about something that's beyond I drink it and I throw it in the recycling bin, right? Yeah. But when you're talking about more industrial grade polymers or industrial grade plastics, now you're thinking a little bit through that life cycle and saying not only how is it going to affect people and how is it going to affect the environment, but what's going to happen to this when it's done? Can I reuse it in my next version of the product? Can I not just recycle it and, put it into the blue container, but can I ask people to send it back to my company so then I can put it into the next generation of the product that we're selling? So that's why, the thing about plastics is that I think it's really important to understand, what polymers and what plastics are in your world. How are they impacting you? What are the ways that you can, curb your exposure to these endocrine disrupting chemicals? But then what are the polymers out there that have actually gone a lot of research into them to ensure that they are safe, to ensure that they are better for the environment and for the individual. And I think, my biggest takeaway of that is the importance of education. I think, the woman that actually, made the documentary happen, not only did she show us how you can get rid of these endocrine disruptive plastics in your home, but she showed us the impact. And, something that she also said, which I thought was really important, is this is not a double-blind study. It's hard to get a lot of conclusions out of it. This is a preliminary study to say, okay, can we actually get funding in order to do a real study of this? And I think something that it highlighted that cuts across science is the importance of being able to research polymers, materials, toxins, chemicals, all these things that sometimes can sound like dirty words or things that don't matter or things that, maybe, oh yeah, I trust it because there's an ad.
Mm-hmm.
Mi familia, they see an ad on TV. My mom will call me and say, oh, have you tried this? I just saw an ad that says it does this and this and this.
Sí. Así mi mamá me manda un video. Gadiel, yo quiero comprarme esto porque mira lo
que hace, mira esto. I'm like...
No research at all.
No research at all?
Yeah.
No nothing. No FDA approved. No nothing.
She sees a Facebook video y me lo manda por WhatsApp y ahí yo tengo que ir para ese doctor.
Yeah. No, exacto. Eso es lo primero. Entonces, the importance of education and the importance of saying we need funding to run these studies, to have the research, to be able to say what is what, because a lot of the times, the only funding that this is going to receive is from public entities.
Yeah.
It's from the National Science Foundation.
Yeah.
It's from the National Institute of Health, because they're the ones that have the funding to be able to do this, and private companies don't have as much of an aligned incentive to be able to do this.
They won't care about getting something. That's how politics is important. The government or if the administration is really willing to fund these types of research that is very beneficial to its constituents, because we could hurt people. Exactly. With certain materials. Right now we're dealing with that with the AI company, which is a whole nother
a whole nother can of worms. Yeah. But I think in general, my biggest takeaway was what happens when you make information accessible, right? What happens when you make a documentary on something that people aren't, gonna go and read a scientific research article about it. These couples had been trying to have a child for over 2 years. I'm sure we're digging in the literature. We're trying to figure out how to make it better. But all they needed was access to a little bit more education, trying something new, trying something alternative that allowed, those dreams to come true. It wasn't, a perfect one-for-one solution, but it allowed them.
We saw a change.
But we saw a change and we saw an impact. Yeah. And I think that's really what I'm excited to see is, can we get funding, not just for the research, but to create media that allows people to be educated? Can we have more media that talks about physics? Can we have more media that talks about materials, not just to excite the next generation of doing it, but so my mom can see it and say, maybe I shouldn't drink, 18 plastic water bottles every day. Or like, if I do, what are things I need to be looking out for? And again, like, this is not my field of research. So I like to say that very clearly, because this is a lot of the same way you're talking about it as popular science. In many ways, I'm talking about it as well. But I think what's really important is just that access, like access to the education, access to the funding for the research, access to the funding for, media creation and these conversations to even be had, which, are often left by the side.
All right. So you're saying that you want to come back and do this whole podcast in Spanish. That's what you're saying?
Let's do it. Yeah, let's do it. I just need a little more prep time.
Hey, I wanted to sit down with somebody that I've been yearning to have this conversation for a very long time, to be honest with you. And when you told me that you study physics, no, we're going to have a conversation. and you're here in my living room having this conversation now.
Great time.
Yeah, Camila, what you want to let people know? How can people follow you? How can they support in what you're doing? And let them know right now.
Yeah, absolutely. So this has been a pleasure, honestly. I think, I've always been inspired by talking about science and communicating science in a way that makes it more accessible. Sometimes it was really hard to, get through those physics classes, feeling like I didn't really have a lot of people to look up to that looked like me, that shared in my story. So yeah, please do reach out. You can find me on Instagram as Camila Uzcategui, and you can find me anywhere on social media with that tag. But please reach out if I can ever be helpful. Let me know, and continue to follow us through our Manifest Technologies journey as well.
Let me tell you something. You inspired me once I met you. You inspired me. I was like, I'm gonna go get my degree. But there's probably a young Latina or a Latino listening to you right now and hearing all of this, you're like, oh my God, you probably inspire somebody. And hopefully we were able to inspire somebody. But like, this is something that I would love to study and get into it. And this is why these things are important. So thank you for being here today. Write in the comments what you think about this podcast. Give it a 5-star. Make sure you guys subscribe. Thank you for joining. Join the conversation. Lo quiero mucho y que la pase bien.